the core Tron API. So all the APIs are implemented via a nonce hijack of virtual alloc. So what does that mean? That basically means there are two roughly 32-bit keys that are handed to virtual alloc. Tron detects this in the kernel and says, okay, this is meant for me as opposed to the kernel, redirects it to one of these APIs. The idea is that you can control these nonces basically consist of a secret key that's your key to Tron and prevent people from being able to write detectors into their software that scan for these APIs. So you basically have an almost 64-bit secret key into Tron. And the APIs are as follows. You have an add cloak, which basically sets up a cloak range from start to end, backed or faked by this start to end range here. And you can do this out of process. The fake memory is actually copied into the kernel and allocated in the target process. So you can use your local stack, you can use heap and free it doesn't matter. And all the virtual locking and the copy on write elimination are done for this API. I should also note that start and end probably should be page aligned just to keep yourself sane, but the kernel will page align these for you. Then you also have remove cloak, which removes your cloak, eliminates any associated permissions that you set up below from that thing, and allocates any injected memory as well. So then you have the permissions APIs, which basically provide with a range of code that is allowed to access a range of cloak. These addresses need not be page aligned, but the cloak, again, probably should be page aligned to keep yourself sane. And then remove allowed will remove that range of allowed code. And you don't have to worry about cleaning up a process exit. I hooked a ZW terminate process, and that eliminates all your cloaks as soon as the process exits, and double check to be removed when Tron is unloaded. Oops. Okay, so we have here's a core usage example, which should be the craziest looking diagram so far. You have on this side, you have allowed code between A1 and A2. This is the left side in case mouse pointer isn't working. Should be between A1 and A2 is going to be allowed to access your evil code over here. Evil code is allowed to access itself, and then other code is going to be given unmapped memory. And this is all done with just 3 API calls. You include the Tron header file. You add the cloak between C1 and C2, saying that it's going to be backed by null memory. And then you add allowed between C1 and C2 to access C1 and C2. And then you also add allowed between A1 and A2 to access C1 and C1 to C2. So to make things even easier and even a little bit more helpful for you, there's some convenience APIs, just to make your job a little bit easier. We've got some high DLL by name and handle. These things take a WCHAR or wide string, Unicode, whatever you want to call it, name, or a load library base address handle for a DLL, and then some fake memory can also be null cloaked. And then hides that whole DLL, edits the module list for you, and uses the WinXP offsets in the module list to delete that thing from the module list. Because if you're working out a process, you probably want to work with the name instead of the handle version because of rebasing that could happen if you load library from a different process. Also, say this now, permissions don't really make sense to allow one PID to access the address space of another because the only way you can do that is through the kernel, through a system call. So we also provide write hidden and read hidden APIs that allow you to access another process's hidden memory. So I mentioned A shadow walker doesn't really deal with race conditions, so that would imply that Tron does. So in fact, it does with a little bit of help from the user. So basically, the idea is you give you say before and after your hidden code is running, you have the option of calling change trust, which basically flushes the TLBs and will prevent job-based scan from being able to detect you running on the same thread. So to visualize this, if you have a queue of jobs and you've got your cloaked code, that is going to happen in one job, and then you know that the scanner can come before or after you. You don't want the scanner to prime the TLB with the fake memory before you access it, and you don't want yourself to prime the TLB with the valid memory before the scanner accesses it. So you want a change of trust. You want to flush your TLBs before and after your code runs if you have a job-based system that you're dealing with. Also, there's the issue of inter-thread scanning as opposed to intra-thread scanning, where you could have a dedicated scanner thread that could happen. And as I mentioned earlier, context switches between threads do not flush TLBs, so you need to do something about that. So basically, this API is provided. You give it the address of swap context from IDA in order to patch this the task switch function in the NT kernel, in order to flush your TLBs always and not just on a thread or not just on a process switch. The reason why it's from IDA is because the NT kernel is rebased on occasion. So the IDA uses the PE headers, which are based at 400,000 and are constant, and then the Tron actually calculates the real base offset in order to patch this properly using the address that you give it. And this uses one of the APIs from librootkit that I'll describe in a bit. So miscellaneous tricks. As I mentioned, there's no hooks. The system calls virtual query especially to lie about the virtual memory areas. The kernel also is not trusted. This is very important. You don't want your target app to be able to just reprocess memory on itself and be able to use the kernel instruction pointer to access trusted memory. So that's a key feature. That reprocess memory is going to give you fake memory. And then memory permissions are also enforced, the write, protect, and what have you. So there are some weaknesses to Tron. The first one really breaks my heart. I think it's the worst weakness, and that's the hidden code doesn't run in VMware. I want to call this a VMware bug, because their IRET doesn't maintain the ITLB. It flushes the ITLB or its virtual copy of the ITLB upon return to userland code. This should be a perf bug. I mean, if there's a page fault happening in your code now, they've got to also do the translation for the code as soon as it returns as well, and get that back into the ITLB again. I don't know. I haven't submitted it to them. If there's any VMware people in the audience, maybe you could do me a favor. It would be really nice to be able to use VMware with this. But data hiding does work just fine. Also, it doesn't really crash VMware, or maybe it does if that'll motivate you guys to look at it. It causes a CPU hang, sort of. So that's VMware does remain responsive for the most part. So as far as detection, there's really only one major way I'm aware of, other than trying to probe the APIs to see if they behave differently, which we did try to take care of to the best of our abilities. Maybe we missed. Hopefully the API should behave normally. The regular APIs I'm talking about, the reprocess memory, virtual query, write process memory, and so on. But this breakpoint verification is also possible. It's basically the same idea that you have when you're trying to detect a userland debugger normally. You set a breakpoint, you install an exception handler for it, you jump to the breakpoint, and if your handler doesn't run, you know that either a bugger is attached and absorbed the breakpoint exception, or something else strange happened. And in this case, something else that's strange happened is Tron is presenting a fake view of your memory, and the breakpoint is being written to the fake memory as opposed to the actual code that's going to be executed when the code jumps to itself. So this only works if you're presenting memory as mapped. If you have null closed memory that is invisible, then touching it is going to give you an access fault, and it's not going to be visible. Okay. So there's some room for improvement. Tron's not perfect. Not sure how much, if any, of this I'm going to do. Some of it is relatively easy. Like so, SMP and HT safeness is different, but probably a bit easier than 64-bit cleanliness at this point. Probably the easiest one on this list is making the API reentrant or thread safe. Right now, there's no locking on any of Tron's data structures. I just sort of depend on the fact that you're not going to be like running lots of crack copies of software on your system at the same time, or rather, more likely not debugging something that you also have hidden code in, but maybe that's cool. If that is happening, I don't know, try and get around it some other way, file system locking, or hey, write a patch, lock down the data structures for me, and I'll take it. Or if it bothers me, maybe I'll do it. We'll see. So far, it's not been an issue. Okay. There's also it says not 64-bit clean. There's a fair amount of 32-bit assembly. The whole page file handler is still assembly. A lot of that probably could be redone in C, actually. But also, you have to clear interrupts and some other nonsense. Clear the WP bit in assembly, so that at least has to be done. Also, I'm really sloppy about mixing V words and P voids. That's done all over the place. That has to be cleaned up. U-longs, too. They're all the same to me. So 64-bit, so 64-bit code is going to require that. Also, a patch guard break probably will be necessary, or you got to with a freaking kernel debugger, or boot into safe mode, I think. That's not very much fun. So that has to be done. So optimizations. Right now, Tron, on every page fault, is going to search all of its hook tables. So a couple of ways you can improve that, considerable hit if you have a lot of cloaks, is if you borrow a bit from either the proto-PKE bit, which is used to shared memory in the Windows kernel, or shared libraries in userland. That bit can be borrowed to try and hint at, or the reserved PKE bit you can try and hint that a PKE is cloaked at Tron, and only search your hooks in the event that those bits are set. So you still have to search your hooks in the event of faults to actual shared memory, but at least you'll eliminate some of them. If that reserved bit is available and not bug checked, you can actually eliminate almost all of them if they don't use that at all, but that's a big gamble. And these things, I think, are documented. These bits are documented in the Reactoless NDK. Has those filled out for you, so you can have a look at where they live, if you're curious. Also making the hook arrays in task tables. It's just a linear search right now because I want things as simple as possible. At least make sure it